Chapter 12, about spectroscopy. And we're going to begin with a bit of an introduction to spectroscopy in general, and then talk more specifically about the two most important forms of spectroscopy for the organic chemist, infrared and NMR. And so let's do that. Spectroscopy. You've all had something of the basics of spectroscopy by now. Spectroscopy itself is, as written up there on the slides, and again, if you miss things, I will post the slides themselves to D2L when I know how many I actually get through. I don't like posting them early because I never know how far I'm really going to get. But I will post these in case you miss a word or two or even more, so you can look for information later on. And presumably a video as well with the slides incorporated in. But at any rate, so spectroscopy is really a study of how electromagnetic radiation interacts with matter. And that's all it is. That sounds very simple, doesn't it? Right? That's all it is. There are a couple basic equations, and here's where I know you've seen these before. And other than a little bit of exercise in some of the homework problems, you probably won't be tested on these directly. But do remember the relationships, right? That's the important part. In Gen Chem and probably physics and other science classes, you've already proved that you can work these equations. But the important thing is what the equations tell us about the relationship of each of the things in the equation, right? So let's just look at that quickly. E equals h nu. That's not a V. I'm not part of the grammar police or anything like that, but one thing that does usually get me is that the Greek letters are substituted by American letters, English letters, whatever you want to call them. And most people say this is E equals HV. It's not. It's E equals h nu. Nu is a Greek letter. So if somebody ever comes up to you, this afternoon and says, "What's new?" You can say, "Well, it's E over H." Toss a little algebra at them. Okay. Anyway, so what's the important relationship there? Of course, H is Planck's constant, so that's a number, always the same number, right? So it's that energy is proportional to what? What does nu talk about? Anybody remember? Frequency, right? Energy is proportional to frequency. As frequency goes up, so does energy. The other relationship, C equals lambda nu, not C equals upside down Y times V. So C equals lambda nu. Again, C is a constant, right? Speed of light. Now this was an inverse relationship though, because both the variables are on the same side. Lambda stands for, anybody remember?
Wavelength.
Wavelength. So wavelength is inversely proportional to frequency. As frequency goes up, what happens to wavelength? It goes down. So those two relationships are really what you need to remember. Not so much the equations, although they're helpful for remembering the relationship. All right? And then here's the thing that matters to us. From the perspective of us, while you're in this class, you are all, by the virtue of the power invested in me by the state of Pennsylvania, I guess, you're all honorary organic chemists. So why does this matter? Well, spectroscopy can be used to determine unknown molecular structures. Wow. That's pretty cool. And the two spectroscopies that we'll talk about in here are the most important for organic chemists to solve molecular structures. Infrared and nuclear magnetic resonance. Usually we just toss out letters, IR and NMR spectroscopy. And by the way, the latter of those two has a variant that's used in the medical field. It's MRI. It's the same thing. It's not done the same way. We can talk about the differences if we have time. But they are, in principle, the same exact technique, just applied differently in a different situation to really get the same information, but the information is presented in a different way. All right. A couple of other things on the slide, of course. There's a bit about units, right? These are the units that are most often used in wavelengths. And also, if you don't quite remember exactly what a wavelength is, there's a graphic there to remind you. Pick any, within a wave which has a peak and a trough, pick any 2 points that are the same on different peaks, of course. So the peak of one compared to the next peak, measure that distance, you have wavelength, right? Okay. Questions or anything about that first bit? That ought to be all by way of reminder, right? You guys all saw this before. Please move faster. You're saying to yourselves, I'm falling asleep. Yeah, okay, good. Let's move a little faster. This is one of those, it's kind of a nice way to present some of this information as far as magnitude goes. This comes out of your textbook. I grabbed different graphics from different sources to try to get points across in this PowerPoint. So this one is out of your textbook. And of course, in the middle column here, you've got the electromagnetic spectrum written a particular way, presented a particular way. Radio frequency down here, visible light there, cosmic rays up there. So as you go up, frequency is increasing, wavelength is going down. Did I get that right? Yeah, there's the frequency arrow. And remember, frequency and energy, they go together. If one increases, the other increases. Wavelength runs the other way. But the fun thing about this one is what's over here in this far right column. They're physical objects that are approximately the same size as that wavelength. Radio waves, about the same size as a whale. And then human height, a cat. That's kind of nice. But just, I don't know, it's kind of a fun thing. Sort of gives you something that you see on occasion. I don't know, when was the last time one of you saw a whale? For real, I mean up close and personal. Thursday? What?
No, 5 years ago.
Oh, 5 years ago. I was thinking Thursday. Wow, that was quite a trip. No, but anyway, it just kind of gives you the